Hello, I'm Dr. Sisser of the Mathematics Department, and today's videotape deals with evaluating limits by using L'Hopital's rule. Before we get to L'Hopital's rule, let's review what we already know about limits. So we wanted to evaluate the limit of x squared plus 4 over x minus 7 as x approaches 3. Now this is a relatively simple problem because we're talking about the limit of a rational function. It's a quotient of two polynomials, and such a function is continuous everywhere except where the denominator is equal to 0. So this function is continuous except at x equals 7. So it's certainly continuous at 3, and if you want to find the limit of a function as x approaches 3, it's a continuous function, all you have to do is substitute x equals 3 in. You can find this limit by substitution because it's a continuous function. The limit of x squared plus 4 is over x minus 7 as x approaches 3 is 3 squared plus 4 over 3 minus 7, or 9 plus 4 over minus 4, or minus 13 fourths. As I said, this was a very straightforward problem. Now suppose we wanted to work out, okay, let's try a slightly different problem. Suppose we want to work out the limit of 7 over x minus 2 as x approaches 2. Unlike the previous problem, this limit cannot be evaluated by substitution because we have a function which is not continuous at x equals 2, because you would have division by 0. Okay. We notice that as x approaches 2, the bottom is going to 0. The top is staying constant 7. Fortunately, we have a method for handling problems like this. We learned that the limit of f of x over g of x as x approaches a, okay, it can be evaluated in the following way. If it turns out that the bottom is going to 0 as x approaches a, and the top is approaching a constant which is not equal to 0, a constant k which is not equal to 0, then this limit, first of all, does not exist. This limit will be either plus or minus infinity, where the sign of the infinity depends on the sign of k and whether g of x approaches 0 through positive or negative values. And we'll discuss how we would determine that in a moment. Okay, so if the bottom is going to 0, but the top is not going to 0, it's approaching some constant other than 0, first of all, this limit does not exist. We know automatically the limit does not exist. But the answer is infinite. It's plus or minus infinity, where the sign of the infinity depends on the sign of the constant k and whether the bottom is going to 0 through positive or negative values. Okay? Now, to understand this further, let's look at this problem as x approaches 2 from the right, and also as x approaches 2 from the left. This little plus means approaches 2 from the right side of 2. Now, as x approaches 2 from the right through values greater than 2, okay, as x approaches 2, the bottom is going to 0. The top, of course, is staying 7. 7 over something which is approaching 0, from what we've just discussed, is going to be infinite. We have to figure out the sign of the infinity. As x approaches 2 through values greater than 2, for example, 2.1, 2.01, 2.001, it's getting close to 2, but always bigger than 2. The top is positive, of course, here, but the numbers that are greater than 2, when you subtract 2, you're approaching 0, but you're positive. So this is positive over positive, so the sign of the infinity is going to be plus. On the other hand, if you want to evaluate 7 over x minus 2, find the limit as x approaches 2 from the left. Once again, the bottom is going to 0. The top is staying a positive number. But now, as you approach 2 through values less than 2, numbers that are less than 2, like 1.9, 1.99, use that as a testing value. Substitute in the 1.9, 1.9 minus 2, it's getting close to 0, but it's negative. Plus over minus, so it's going to be minus infinity. So, if you have a problem where the bottom is going to 0 and the top is not going to 0, you want the limit. First of all, this limit does not exist. If you want to know further information about how it does not exist, we can investigate what happens as you approach 2 from the right and from the left. A good idea would be to take a testing value, a number which is close to 2 but from the right of 2, say like 2.1, a number which is close to 2 but on the left side of 2, 1.9. Substitute in that value. Whatever the sign of the expression is, that will be the sign of the infinity. Okay? So it's either plus or minus infinity, and the sign is dependent upon the sign of the numerator and whether the bottom is going to 0 through positive or negative values. Okay, now, what if we were going to work out the following problem? Limit, as x approaches 2, of 7x minus 14 over x squared minus 4. Okay? Once again, we cannot find this limit by substitution. This is not a continuous function at 2 because we'd have division by 0. So that's out. Now, when we try to see what happens as x approaches 2, yes, it is true the bottom is going to 0, but unlike the preceding problem, the top is also going to 0. In order to use the theorem that we had just worked with, if the bottom went to 0, but the top didn't go to 0, then we know automatically that limit does not exist. Be plus or minus infinity, and we determine the sign of the infinity by the method I had just explained. Now, but that's only if the bottom goes to 0 and the top doesn't go to 0. If both the bottom and the top are going to 0, this is known as an indeterminate form. Okay? Indeterminate form. In fact, this is known as the 0 over 0 indeterminate form. And in a problem like this, basically anything can happen. You cannot know, it's indeterminate means you cannot call it from this point. Okay? Maybe the limit will exist, maybe it won't exist. We cannot make a decision when it's 0 over 0. Okay? This particular problem, we can do something. If you factor the numerator is, you factor out a 7, it can be written as 7 times x minus 2. And the denominator can be factored, it's a difference of 2 squares, into x plus 2 times x minus 2. Now as x approaches 2, x is getting closer to, it's not equal to 2. X minus 2 is not 0. And since x minus 2 is not 0, you can divide numerator and denominator by x minus 2. And this reduces to the problem of the limit of 7 over x plus 2 as x approaches 2. Now this problem can be found by substitution because this function is continuous at 2. If you want to know what's happening to 7 over x plus 2 as x approaches 2, we may substitute in x equals 2, get 7 over 2 plus 2, or 7/4. So in this particular case, the limit does exist, and the limit is 7/4. Okay, so in this problem, the bottom was going to 0, but so was the top. We said this is called an indeterminate form, 0 over 0 indeterminate form. Anything can happen. In this particular example, the limit turned out to be 7/4. Let's look at a very similar problem. Limit as x approaches 2 of 7x minus 14 over, instead of x squared minus 4, over x squared minus 4x plus 4. Once again, we can't find our limit by substitution because the bottom is going to 0. If you let x approach 2, you'd have 4 plus 4, 8 minus 8. The bottom is going to 0. The top is also going to 0. It's again a 0 over 0 indeterminate form. Anything can happen. If, however, we perform some factoring, we factor out a 7 on the top times x minus 2, and we factor the bottom into x minus 2 times x minus 2. And if we divide numerator and denominator by x minus 2 as we did in the preceding problem, this reduces now to the limit of 7 over x minus 2 as x approaches 2. And earlier today we saw that in this case the bottom is going to 0, but the top is not going to 0, and this limit does not exist. So that's why we call 0 over 0 an indeterminate form. Anything can happen. When you look at a problem and see 0 over 0, you can't assume the limit will or won't exist. In the preceding problem, we had a 0 over 0 form, and it turned out after factoring and canceling, the limit turned out to exist. It was equal to 7/4. In this problem, it started off very similar. It was 0 over 0, but when we factored and canceled, it reduced to another problem. Turned out this limit does not exist. The bottom went to 0, the top didn't. Right away, we know that limit does not exist. So understand that when I say 0 over 0 is an indeterminate form, you really cannot make any conclusion at that moment. You have to work it out further. Of course, we've seen examples where simple factoring and canceling did not help as far as limit evaluation. We wanted to work out the limit of sine x over x as x approaches 0. This was also an indeterminate form. As x approached 0, the bottom went to 0, and the top also went to 0. It was a 0 over 0 form. And we couldn't just factor and cancel. In fact, if we work this out in class, some of you may have seen calculator evaluations of this limit. Some of you may have seen a construction with inequalities and the use of the squeeze theorem to evaluate the limit. Turned out this limit was equal to 1, assuming that x was a real number. We were not measuring our angles in degrees. But this limit was not an easy limit to come by. We had to do a lot of work to find it. It was also a 0 over 0 form. Now, fortunately, we do have an easy way for evaluating 0 over 0 indeterminate forms. That is to use something called L'Hopital's theorem. Now, L'Hopital's theorem says that if you are doing a 0 over 0 indeterminate form, for example, in this problem, we wanted to do the limit of 7x minus 14 over x squared minus 4 as x approaches 2. As soon as you've ascertained that both the bottom is going to 0 and the top is going to 0, you may use L'Hopital's rule, which says instead of this limit, you can work out the limit of the following problem. Take the derivative of the numerator, the derivative of 7x minus 14 with respect to x, that's 7. Take the derivative of the denominator, x squared minus 4's derivative with respect to x is 2x. And see if you can work out this limit. If you can work out this limit, and of course this particular limit can be evaluated by substitution, we can let x equal 2, we get 7/4. If you can work out this limit, then the original problem has the same limit. This is what L'Hopital's rule says. So if you have a 0 over 0 indeterminate form, and you can work out the derivative of the top divided by the derivative of the bottom. I did not say use the quotient rule on this. We do not want to use the quotient rule. Not the derivative of a quotient, but rather the derivative of the numerator divided by the derivative of the denominator. Evaluate that limit. And here we see we get the same answer, 7/4 for here and there. Let's go back to this problem over here and review it from the point of view of L'Hopital's rule. If you wanted to work out the limit of 7x minus 14 over x squared minus 4x plus 4 as x approaches 2, we notice that the bottom, once again, is going to 0. The top also went to 0. This is an indeterminate form. We take the derivative of numerator. The derivative of 7x minus 14 with respect to x is 7. the derivative of the denominator of x squared minus 4x plus 4 with respect to x is 2x minus 4. And we try to evaluate this limit. Well, here, the bottom is going to 0. The top isn't going to 0, so this limit does not exist. Well, if this limit does not exist, then so is it true also about the original problem. The original problem's limit does not exist, which is the same answer that we found. So using L'Hopital's rule here, we got the same answer that we had with factoring and canceling. Using L'Hopital's rule on this problem, with factoring and canceling, we got the same answer. Now let's go back to this problem that we had over here, the one that required all that work in calculus class to evaluate the limit. Using L'Hopital's rule, to 0 over 0 form, we take the derivative of the numerator over the derivative of the denominator. We evaluate this limit. Well, the limit of cos x as x approaches 0 is cosine of 0, or 1. And of course, we get the right answer. Okay, now I don't want you to feel that we've wasted your time in class if you did go through a lengthy proof of this limit being 1. Okay, you can't really use L'Hopital's rule to evaluate this limit for the first time because this is the limit that we use to figure out the derivative of the sine was the cosine. Okay, so you wouldn't know, until you work out this limit, you would not know the derivative of sine is cosine. So it had to originally be worked out that way, and now, of course, we can use L'Hopital's rule in any 0 over 0 form. Let's try another example. How about the limit as x approaches 0 of x minus 2 sine x over tangent x? Now, as x approaches 0, tangent of 0, this is going to 0. And the numerator, 0 minus 2 sine 0, is also going to 0. So it's a good candidate for L'Hopital's rule. We're going to take the derivative of the top over the derivative of the bottom and work out that limit. By the way, if you want, you can put a little h over here, over the equal sign, to indicate that you're using L'Hopital's rule on that stage. Okay, the derivative of the numerator, 1 minus 2 cosine x. And the derivative of the denominator, the derivative of tan x with respect to x, is secant squared x. Okay. Now, some of you may have trouble with secant of 0. It has to be evaluated. So feel free to rewrite secant of x as 1 over cosine x. So secant squared x is 1 over cos squared x. Okay, now we can work out this limit by substitution. Because I only used the h here when I actually was performing L'Hopital's rule. Any kind of algebraic or trigonometric maneuvers that I'm using, I'm not putting the L'Hopital's rule symbol down. Now, this limit can be evaluated by substitution. As x approaches 0, 1 minus 2 times cosine of 0, cosine of 0 is 1, over 1 over cosine of 0 squared, or 1 squared. So we get 1 minus 2, or minus 1 over 1 squared, or minus 1 for an answer. Okay, for our next example, let's work out the limit of x squared minus 3x over x squared minus 4x plus 3 as x approaches 3. First, we try to see what happens if we were to let x equal 3. The denominator would be 9 plus 3, 12, minus 4 times 3, 12, minus 12. The bottom would go to 0. We immediately go upstairs to see what's happening there. The top is also going to 0. X squared minus 3x is approaching 9, minus 9 approaching 0. So we have a 0 over 0 indeterminate form, and we're going to use L'Hopital's rule. We're going to take the derivative of the top, which is 2x minus 3. and divide by the derivative of the bottom, which is 2x minus 4, and try to evaluate this limit. It turns out this limit can be evaluated by substitution. And if we do that, we get 2 times 3 minus 3 over 2 times 3 minus 4, 6 minus 3 over 6 minus 4, for an answer of 3/2. According to L'Hopital's rule, the original problem, which was of 0 over 0 form, its limit is the same as the limit of this new problem, in which we evaluate the limit of the derivative of the top over the derivative of the bottom. Okay, let's try another example. Limit as x approaches 0 of sine x minus x over x cubed. Once again, as x goes to 0, the bottom is going to 0, and so is the top. So we have a setup to use L'Hopital's rule. The derivative of the top is derivative of sine x, which is cos x, minus derivative of x, which is 1, over derivative of x cubed, which is 3x squared. And let's see what happens when we try to evaluate this limit. We notice that in this problem, the bottom is still going to 0, and cosine of 0 is 1, so 1 minus 1, the top is also going to 0. We are permitted to use L'Hopital's rule repeatedly. If we keep getting 0 over 0 forms, we can use L'Hopital's rule over and over again as long as it stays 0 over 0. Okay, so let's work this out. Let's try L'Hopital's rule here. The derivative of cos x minus 1 is minus sine x. The derivative of 3x squared is 6x. All derivatives, of course, with respect to x. And now, as x goes to 0, look what happens. The bottom is still going to 0, as is the top. So, once again, we're going to try L'Hopital's rule. One more time here. Limit as x approaches 0. Let's take the derivative of the top, which is minus cos x. Derivative of the bottom is 6. Now, at this stage, it is no longer 0 over 0. This limit can be evaluated by substitution. Cosine of 0 is 1, so we get minus 1 over 6, or minus 1/6. So, if you have a 0 over 0 form, you may use L'Hopital's rule to evaluate the limit. If you keep getting 0 over 0, you can continue. In this case, we had 3 applications of L'Hopital's rule. Eventually, it came down to something whose limit we could evaluate, and the answer to the original problem is minus 1/6. But you have to be careful. If the problem is the limit as x approaches 0 of 1 minus cosine x over 6x squared plus 3, there's a tendency to use L'Hopital's rule even when it's not appropriate, because you've sort of gotten into the habit. Okay, you may only use L'Hopital's rule if it's a 0 over 0 form here. Now, this particular case, yes, the top is approaching 0, but the bottom isn't. This can be evaluated simply by substitution. As x approaches 0, 1 minus cosine of 0 over 6 times 0 squared plus 3 has a nice answer. It's 1 minus 1 over 0 plus 3, or 0 divided by 3, and the answer is 0. Okay. If you try to use L'Hopital's rule, you would get an incorrect answer. So don't use L'Hopital's rule unless you have a 0 over 0 indeterminate form. Just want to remind you of one thing. If instead of this we were working out the limit of the reciprocal, 6x squared plus 3 over 1 minus cosine x, as x approaches 0. Here we'd have a case where cosine of 0 is 1, the bottom is going to 0, the top would be approaching 3, and this limit would not exist. So we know we can use L'Hopital's rule on 0 over 0 forms. If we don't have a 0 over 0 form, either because, say, the numerator is approaching 0 but the denominator isn't, and like in this case, 0 over 3, that's fine, the answer is 0. Or if we have a case where the bottom is going to 0 and the top isn't going to 0. This is also not indeterminate. This limit does not exist. Okay, so this limit existed, this limit did not exist, but in both cases we could make a decision immediately. It is only on the 0 over 0 form that we had trouble. That was an indeterminate form that we needed to use L'Hopital's rule. Now all the problems that we have worked out so far were in the indeterminate forms were in the 0 over 0 indeterminate form category. There are other indeterminate forms. There's a 0 over 0 indeterminate form, and there's also the infinity over infinity indeterminate form. On either of these, if it was 0 over 0 or infinity over infinity, and I'll give an example of that in a moment, you may use L'Hopital's rule directly. There'll be other indeterminate forms I'll be showing you on this videotape, but only 0 over 0 and infinity over infinity can you use L'Hopital's rule directly on. For example, let's say we wanted to work out the limit as x approaches 0 from the right of the natural log of x over 1 over x. Now, we're familiar with the curves y equals log x and ln x and y equals 1 over x. We know how to sketch the graph of each of these functions. Y equals natural log of x looks like something like this. Y equals 1 over x is the hyperbola in the first and third quadrants. Now, as x approaches 0 from the right side, what is happening to the natural log of x? As x approaches 0 from the right side, natural log of x is approaching minus infinity. So this is approaching minus infinity. On the other hand, as x approaches 0 from the right, what is happening to 1 over x? The y value here is approaching plus infinity. This is known as an infinity over infinity indeterminate form. It could be plus infinity over plus infinity, or minus infinity over plus infinity, or plus over minus, or minus over plus. But if the top and the bottom are each approaching one of the infinities, it's known as an infinity over infinity indeterminate form, and we may use L'Hopital's rule directly on it. The same way we did it on the 0 over 0 form. You take the derivative of the top, which is derivative of natural log of x, which is 1 over x. The derivative of the bottom, the derivative of 1 over x, or x to the minus 1 power, is really minus x to the minus 2, or minus 1 over x squared. And now we look to see what we have. Now, you could say, well, as x approaches 0, the bottom is still infinite, because the bottom is going to 0 and the top isn't. The top is also infinite. The bottom is going to 0 and the top isn't. So you could say it's still an infinity over infinity form. However, that would be a mistake. If you have an infinity over infinity form, after you've used L'Hopital's rule, check to see if any algebraic simplification can be performed. Okay, so you might want to, so this is not L'Hopital's rule, you might want a little a for algebra, or just to know that we're not using L'Hopital's rule now. I'm simply saying 1 over x divided by minus 1 over x squared is 1 over x times, you can invert and multiply by minus x squared over 1. Instead of dividing by minus 1 over x squared, you can invert and multiply by minus x squared over 1. And then you can divide numerator and denominator by x. We have minus x squared here over x. Dividing top and bottom by x, this comes down to minus x squared over x is just minus x. And now the limit as x approaches 0 of minus x is minus 0 or 0. If, however, you had kept saying, well, this is infinity over infinity, and took derivatives again, it would still be infinity over infinity, that wouldn't help you. So always take the time after an application of L'Hopital's rule to see if any algebraic simplification can be performed. And if so, it could be that you're closer to the solution than you think. Let's try another example of an infinity over infinity indeterminate form, limit as x approaches infinity of 6x squared over e to the x. Now, as x approaches infinity, 6 times a very big number squared, this is approaching plus infinity, as is this. E to a very large number is getting very large, so this is an infinity over infinity form. We may use L'Hopital's rule. Take the derivative of the top over the derivative of the bottom. It is still infinity over infinity form, and no algebraic simplification can be performed. So we use L'Hopital's rule again. Derivative of the top over the derivative of the bottom. And at this stage, okay, we have a situation, the numerator is fixed at 12. The bottom is getting larger and larger. As x approaches infinity, e to a very large number, this is getting bigger and bigger. 12 over something getting bigger and bigger, this is going to 0. 12 divided by a million, 12 divided by a billion, the numbers are getting smaller and smaller, so the answer, that's approaching 0. So we have another example of an infinity over infinity indeterminate form, and it led to a finite limit here. Summarizing what we have done so far, 0 over 0 and infinity over infinity are indeterminate forms.